Hello, hackers! Welcome to Hacker 101 iOS File System Basics. In this module, we'll look at how an iOS application's file system on the device is structured and how to analyze the data you find there. If you have a jailbroken device, you can follow along by connecting to your device over SSH as the root user. But if you don't have a device handy, we've also provided a sample file system for you to download so you can test your skills. There will also be a few bonus demos in this module that use more advanced runtime techniques with the device, but they aren't required to understand the material. An iOS application's file system on the device is divided into two paths. I'll refer to these as the bundle path and the data path. If you already completed the iOS Application Basics module, you'll remember that the bundle directory is copied from the application's IPA file and that it is signed to prevent tampering. The destination for the bundle directory is a randomly generated directory under var containers bundle application. Similarly, a randomly generated directory under var mobile containers data is provided to the application for data storage at runtime. Note that the UUIDs generated for the two directories are not the same. Within the application's data directory, iOS provides a number of special purpose directories intended for particular types of data. The documents directory is intended for user-generated content, while the library directory and its subdirectories are for application-generated content that is not intended to be exposed directly to the user. Some of this content, like the data in the caches directory, may be generated as a side effect of the application's features. The application's developers may not necessarily realize what is being saved in these files. In general, it is important that the data is stored in an appropriate place because some of these directories have additional features. For instance, files in some directories are backed up by default. This may not always be desirable, depending on the sensitivity of the data. I've unzipped the iGoat file system to my current directory, and as you can see, it contains the full path that you would see on the device to give you a feel for what you'd normally encounter. I'm going to navigate to the apps directory. You can see that it has a random UUID as the name. In that directory, we have the documents, library, and temp folders. And one folder I didn't mention previously, the system data folder. The operating system may store files in this folder that are related to the app, but the files are not accessible to the app. We can use the find command to view the contents of the data directory for the app. To enable developers to protect sensitive data stored by their applications at runtime, Apple provides per-file encryption through the Data Protection API. There are 4 levels of protection provided, also known as data protection classes, with the lowest being none and the highest being complete. A file's assigned data protection class will determine when keys to decrypt the file are available. For the none class, the decryption keys are always available. For complete until first user authentication, the keys are available once the device has been booted and unlocked, and remain available until the device is rebooted. For complete unless open, decryption keys are briefly available for files that are open at the time a device is locked, but otherwise, the keys are only accessible when the device is unlocked. For complete, the decryption keys are inaccessible as soon as the device is locked, regardless of whether the files are in use. The security of the Data Protection API relies on the user setting a passcode on the device, so it can't be easily unlocked to gain access to decrypted data. For the 2 lowest classes, none and complete until first user authentication, data at rest can be decrypted when the device is locked, but there are some mitigations that prevent direct file system access from being trivial. When a device is connected to a computer over USB, the user must explicitly consent to trusting the computer before it can access the device. That trust can't be established while the device is locked, so a device with a strong passcode should be difficult, if not impossible, to gain data from in this fashion. In fact, Apple's default data protection class for application data has been complete until first user authentication since iOS 7, but this was originally aimed at attacks that require a reboot during exploitation. The problem with relying on this data protection class for sensitive data is that a separate vulnerability that exposes the file system on a locked device could also expose data with this level of protection. How does iOS know what data protection class is applied to each file? iOS uses extended attributes to store the data protection class. Extended attributes are metadata that are stored separately from their corresponding files. Typical tools that are frequently used to exfiltrate application data from a device don't capture the extended attributes, so it becomes necessary to examine these directly on the device instead. There are 2 ways to go about that. We can use a tool that is aware of extended attributes to examine the files, or we can ask the application to tell us about the files at runtime. For this demo, we'll be asking the application to tell us about the data protection classes applied to its files. I have my iPad connected to my laptop via USB, as can be seen using the frida ls devices command. I'm going to use the frida CLI with the code share feature, which allows you to pull down code shared publicly by other developers. I've chosen to load the iOS data protection agent script by the user AK, which will inject the script right into iGoat for me. This makes two functions available in the CLI that can show data protection classes. I'm going to choose the one that will dump the classes for all paths in the app's data directory. The output from the script shows the data protection class for each file. You can see a lot of these are complete until first user authentication. But some are complete unless open, or even none. iOS provides storage APIs that are important to understand and recognize when analyzing applications. We'll take a closer look at NSUserDefaults, core data, and NSKeyedArchiver in more detail. In the iOS Application Basics module, you learned about the info.plist file and the property list format. The NSUserDefaults API also stores data in a plist file under the Application's Preferences directory. This API is intended for simple key value storage and can directly store primitive data types like integers, floats, and booleans, and a small number of built-in object types like arrays and dictionaries. More complex data types that aren't directly supported need to be serialized to a compatible format. Because iOS brokers access to the plist file that stores the application's preference data, developers may not realize that the file itself has a data protection class of complete until first user authentication. This is appropriate for non-sensitive preference data, but doesn't offer sufficient protection for storing passwords, personally identifiable information, or other sensitive user information. There is one preference plist file in the iGoat data directory. If we use the macOS plutil command with the -p flag, we can decode the plist the same way that we did with the info.plist file in the previous module. If we try reading it directly, we see some garbled strings for the most part because this file is in binary plist format. The information here isn't too interesting, but it would be a good idea to check it after interacting further with the application. For data that is complex but still structured, core data offers a database-backed model for storage. You'll typically see core data files in the application support or documents folders. The database used by core data is called SQLite. SQLite is fairly common on mobile platforms because the database is self-contained in a single file and easily portable. Most of the time, SQLite files will have a .db extension, but core data uses .SQLite. The interesting thing about SQLite is it uses a write-ahead log in a separate file to record changes to the database. As a result, the WAL file may contain interesting data that hasn't been written to the database file yet. When you connect to the database, the changes from a corresponding WAL file may be written out if it is present. As a result, I usually make sure my files are backed up before I analyze them, and I analyze a copy of the database in isolation without the WAL file to make sure data isn't deleted or overwritten. Let's take a look at some commands you can use to examine the contents of a SQLite database. The core data files are under Library Application Support, where we would expect to find them. I'm first going to back up the write-ahead log file so we can look at it separately later. The first SQLite command we'll use to examine the database is the .schema command. This will dump the database schema, and based on this, you can tell pretty quickly that this is a core data file based on the z_ prefixes. The next important command is .dump. This will dump the contents of the database, printing out each command that was used to create and populate it. Just from dumping it, we've already found a piece of interesting information. If we dump the strings from the database, we can still find the username and password, but lose some context. There's also a bplist string. Remember that we saw that same string looking at binary plist files. The hex-encoded data we saw in the database dump probably contains a binary plist file, which we could extract and further decode. What about that wall file? Dumping the strings there reveals the username and password again. You can see from looking at this example that core data is useful for structured data. For serializing arbitrary objects to disk, you may see applications use NSKeyedArchiver. NSKeyedArchiver can be used to store the class information and instance variables for one or more objects to a file. Files with NSKeyedArchiver data can be written anywhere in the application's data directory, and to complicate it further, the files are in a property list format but do not necessarily have a plist extension for easy identification. The values in the file may be further encoded in base64 or ASCII hex, or may even be in a binary plist format, so it can be easy to miss contents that are sensitive. Let's take a look at what an NSKeyedArchiver file looks like and how to decode it. If we look for the string NSKeyedArchiver in the data directory, there are a number of files that match. It is a popular serialization format. Let's take a look at one of the flurry files. Looks like another binary plist. Usually plutil would be useful here. But even after decoding it, it doesn't make much sense. There are some clues that there might be interesting data here. Let's try deserializing it instead, using a Python script I call deserial. Now we have a readable key value format. We can see there is an API key embedded here, along with some information that was probably gathered when the application ran. There are two other types of files that you'll see in many iOS app file systems. Unlike the storage APIs we just reviewed, these two file types are a side effect of normal application behavior. The first of these is the binary cookies file. On iOS, each application maintains its own cookie store for networking APIs like NSURL session. Persistent cookies, those with an explicit expiration date, are stored on disk under the cookies directory. The format of this file is the same as that used by Safari on the Mac, and is a binary format that can be parsed and decoded to examine the cookies stored there. By default, iOS sets the data protection class of the binary cookies file to complete until first user authentication, so any sensitive cookies, such as those that authenticate the user, can be decrypted after the first unlock after reboot. Let's take a look at a raw binary cookies file and try decoding it. We can use the xxd command to hex dump the cookies file. There's some readable strings there, and once again, an appearance by a binary plist. Now let's use the binary cookie reader script. After decoding, we can clearly see the cookie attributes, including the expiration date. The last type of file that we're going to look at is the on-disk cache file used for NSURL cache, which caches requests and responses obtained through the URL loading system on iOS. Data in the cache is stored as binary plist blobs in a SQLite database under the caches subdirectory. Usually these files will be named cache.db, but they can appear under other names. The default behavior of the URL loading system is to obey the cache control headers that are sent in server responses. If those headers are absent or allow caching, the request and response data are stored in the database. This can include sensitive information, so the cache is a good place to look for passwords, session tokens, and personally identifiable information. The quickest test you can perform with the cache is extracting strings and looking for known sensitive information, such as grepping for the password you use to log in. However, if the application might cache sensitive images or files, reconstructing the response data is a good idea. For instance, consider a healthcare app that allows users to view scans of their test results. The database file itself only stores responses up to a certain size, but larger files are conveniently stored in the FS cache data subdirectory. You'll know to look for a downloaded file for a particular request due to a field in the cache called isDataOnFS. This will be set to 1 when the data is stored on disk. Let's use a SQLite 3 command to examine the basic structure of the cache. Then I'll show you how to process the data in the cache using a simple Python script. I'm starting off in the cache's subdirectory of the file system. We're going to navigate to the directory named for the apps bundle identifier. You can see that the 3 cache files we expected are here. Let's first check the schema of the database file using .schema. Multiple table names shown start with CFURL, an indication that we are looking at an NSURL cache. It's not entirely clear from the schema what data we might find in the tables, so let's dump the contents of the database with .dump. One thing that might catch your eye at the top is the isDataOnFS field in this table. Recall that it will tell us if the data is in a file on disk or stored in the database. In this case, the value for the field is 0, so we know that the contents are in this row. If we eyeball the data that was dumped, most of it is hex encoded, so we need to decode it to read it, assuming it is string data. We can run strings on the file for a quick look. That gives us some additional clues. There is a URL here and an indication that some of the hex-encoded data we saw is in binary plist format. If we scroll down a bit, there is some clear text data that looks like it might be a credit card number. A little bit further along, we see some HTML that might be part of a server response. We're getting somewhere, but it would be even better to see the raw requests and responses so we can get the full context for what we saw in the file. I'm going to use a simple Python script to query the data from the database and arrange it in a more readable format. After the script runs, there will be a dump directory that contains one request and response pair per file. Now we can examine the requests and responses in full. Remember, by default, these cache files are not encrypted, so any sensitive post data, cookies, tokens, etc. can be retrieved if the file itself can be exfiltrated from the device. You now know how to recognize and analyze some of the most common iOS application artifacts. Since applications are evolving all the time, here are a few general tips that always apply. Remember to review the file types for the application's data to help you prioritize your analysis. Keep track of the sensitive information you enter in the app and search the contents of the application's data to see if any of it is stored insecurely. Finally, while we've been focusing on data storage in this module, don't skip over files that just look like binary data or code. Run strings on binary files and review the contents of code files to see if you can identify any weaknesses. Make sure to check out our next module on iOS inter-app communication. You'll learn about 3 key ways that iOS applications use to communicate with each other, and how to identify vulnerabilities in that functionality using runtime instrumentation. Until then, happy hacking!